Bacteria may hold the key to fighting off certain viruses in patients once and for all. In a new study published in PLOS Pathogens, researchers in the Netherlands used the hot new genome editing system known as CRISPR-Cas to target herpes viruses, some of the most common and persistent viruses that infect people. The technique, which is based on a bacterial defense mechanism, works in human cells to limit replication of the herpes virus, and in some cases, even allows for their complete eradication. Herpes viruses are all around us. The family includes the herpes simplex viruses that cause cold sores, recurrent eye infections, and genital herpes, as well as others that can cause birth defects, spread mononucleosis, or cause cancer. Nearly all adults are infected with at least one of them, but many people probably don't know it. That's because the viruses are very good at staying under the radar and out of the way of our immune systems. During flare-ups, the viruses pop out more copies of themselves and can be treated with existing antivirals, but those drugs can't eliminate the virus. The infection is lifelong. The CRISPR-Cas system offers one way to seek and destroy these latent viruses. Short guide RNAs can direct the Cas9 protein to specific viral sequences, allowing it to break the DNA at precise locations. This editing is so damaging that it kills the virus. If it can reach all existing copies, it's a potential cure. The Dutch researchers first tested whether CRISPR could work against Epstein-Barr virus, which causes mononucleosis and drives certain cancers. They designed guide RNAs to target several critical viral genes. In a model of latent EBV infection, they found that single guide RNAs, together with the Cas protein, successfully removed the virus in 40 to 60% of cells. Using two guide RNAs sequentially worked even better, leaving more than 95% of cells virus-free. Next, the scientists turned to human cytomegalovirus, or HCMV. It's responsible for birth defects and can be deadly to people with weak immune systems. CRISPR successfully limited viral replication, but it was important to choose the right targets. Guide RNAs against inessential genes failed to slow viral reproduction, and different strains of HCMV were more susceptible to some guide RNAs than others. In human cells infected with herpes simplex virus type 1, CRISPR also blocked viral replication. In contrast to HCMV, even when the researchers targeted non-essential viral genes, it still worked, although to a lesser extent. Using two guide RNAs again proved to be most successful, in part because two targets make it harder for the virus to mutate and escape treatment. While virus titers from infected cells fell by as much as 10,000 times with a single guide RNA, viruses were undetectable in dual-treated cells. CRISPR could also block replication of reactivated virus, but couldn't edit latent virus. HSV-1 viral genomes persisted despite treatment. The results suggest that CRISPR is an effective way to limit replication of multiple herpes viruses, but the holy grail, eradication, so far is only possible for Epstein-Barr virus. One reason for this difference might be the availability of viral DNA to the CRISPR system. EBV's genome is located in easily accessible circular molecules within the nucleus of dividing cells, whereas HSV-1's genome is closed off in non-replicating neurons. Future work may reveal a way to target latent genomes for HSV-1 as well. Until then, anti-herpes virus CRISPRs have several promising applications that await testing in animal models or humans. They might remove cancer-causing EBV from tumor cells, help rid donated organs for immunocompromised patients of viral invaders, or prevent cold sore outbreaks and recurrent eye infections by blocking HSV-1 reactivation. All thanks to the defense mechanism of bacteria.